Welcome back to Mechanical Engineering Made Simple. Today, we're really taking a step back. We're doing a deep dive into the process that, well, kind of runs underneath everything in modern technical design.
Yeah, moving beyond just the components themselves.
Exactly. We're looking at the organizational brain, systems engineering, dynamic modeling, and maybe most importantly, the control systems that make complex machines actually do what we want them to.
It's all about managing complexity.
That's the goal. We want you to walk away with some quick but really solid knowledge about how engineers get a handle on these massive, intricate projects, how they make sure things actually succeed.
And it's interesting how the source material defines systems engineering right off the bat. It's not just equations and diagrams.
No. What is this?
It's framed as the right mix of mathematical theory, yes, but also behavioral and management ideas, all brought together to tackle these big, messy, real-world problems.
Percy, how?
Well, problems with large scale, wide scope, and crucially, involving information that's often incomplete, uncertain, maybe even just plain imperfect. It's about making sense of that.
Okay, let's unpack this a bit because that sounds huge, like solving global crises. If that's the big picture, what's the actual day-to-day mission for an engineer using systems engineering? Where does it even begin?
Right. The functional mission is much more concrete. It's really the art and science of producing something. Could be hardware, could be a service that performs its function, is reliable, high quality, trustworthy.
The basics you'd expect.
Yes, but here's the kicker. Doing all that within the cost and time constraints you're given, that's critical.
So the perfect machine built too late or too expensively is actually a systems failure.
Precisely. The process failed, even if the machine itself is brilliant.
Okay, so thinking about that process, that product life cycle, from idea to reality, what are the absolute essential phases we need to understand?
Real-world projects break down into lots of steps. Concept, planning, detailed design, testing, you name it. But fundamentally, it really boils down to three core stages.
Which are?
Definition, then development, and finally, deployment. That's the basic arc from what do we need to here it is, working.
So definition, development, deployment. Got it.
And if there's one nugget to really latch onto here, it's this. That first phase, the definition phase, specifically the requirement specification part, that's arguably the most critical step in the entire journey.
Why so important?
Because its goal is the detailed definition of the needs, the objectives, the things the system absolutely must fulfill. Get that definition wrong or incomplete.
And everything that follows is built on a shaky foundation.
Exactly. The quality of that requirements definition heavily influences everything downstream. You could have the world's best engineers optimizing perfectly for the wrong goal. That's an expensive way to fail.
Makes total sense. Garbage in, garbage out, as they say. So how do engineers actually dig out these requirements, especially when things are complex, when maybe the client isn't even totally sure what they need yet?
That happens right at the start in what's called the issue formulation step. It's about defining the problem clearly and also designing the value system, figuring out what the client really values. Is it speed, cost, safety?
And how do you find that out?
The sources give us a few methods. First, the obvious one, just asking.
Talking to people.
Right. Direct declarative approach. If the uncertainty is low, the problem's pretty well understood, you go to the experts, the stakeholders, and you ask them what the system needs to do.
Okay. Seems straightforward enough. What else?
Second method is descriptive identification. This means you study existing, similar systems, very common if you're upgrading something.
Like looking at the old version to design the new one.
Exactly. But there's a big caution here. This approach often leads to only small incremental improvements.
Why that?
Because you risk getting anchored to the old system. You might accidentally carry over its limitations, its bottlenecks, maybe even flaws you didn't realize were there into the new design.
So you end up designing a slightly faster horse when maybe you should have been thinking about a car.
That's a perfect analogy. You optimize based on yesterday's problems, not tomorrow's needs.
Okay, so asking, descriptive identification. That's the third way.
That's normative synthesis. This one's more forward-looking. It involves studying things like future planning documents, upcoming regulations, industry standards, trying to figure out the desirable objectives for a system that maybe doesn't even exist yet.
So trying to anticipate the future needs.
Right. Now, once you start gathering all this stuff, requirements, components, objectives, constraints, it can become overwhelming. Hundreds of interacting pieces. How do you possibly keep track?
Yeah, how do you avoid just drowning in details.
You have to impose structure. You need to map out the connections, make the complexity visible. Listing parts isn't enough. You need to see how they influence each other.
What tools help with that?
Interaction matrices are really powerful. Think of a big grid, like a spreadsheet. It lets you systematically map the relationships between elements, maybe objectives versus design alternatives, or subsystem A versus subsystem B.
So you can see hidden dependencies.
Exactly. Oh, changing this affects that over there. And the other key tool is using trees.
Like organizational charts?
Sort of. They're graphical ways to show hierarchy or branching structures. Think work breakdown structures or functional decomposition, breaking a big function down into smaller and smaller pieces. It just makes the whole thing easier to grasp, easier to communicate.
Which is vital for keeping a large team on the same page.
Absolutely. Everyone needs to be building the same thing for the same reasons.
Okay, requirements are defined, structured. Now, this is where, for me at least, it gets really interesting. We move into dynamic modeling, core mechanical engineering stuff. But why bother with abstract math models? Why not just build the thing and test it? Isn't simplifying it with a model, like, inherently less accurate, maybe even negligent?
That's a fair question, and it gets asked a lot. But the reason for modeling is actually very practical. It comes down to accessibility.
Accessibility.
Yeah, a mathematical model is just way more accessible than the real physical system. It's much less expensive to create and run. It's faster. It's far easier to modify.
Now, safer to test extreme conditions, I imagine.
Definitely. You can simulate failures, push boundaries, ask all sorts of what-if questions, even about systems that haven't been built yet, without breaking expensive hardware or, worse, causing accidents.
Okay, that makes sense from a practical standpoint.
And here's a key takeaway from the sources on this. The best engineering model isn't necessarily the most complex or the most accurate one.
Really?
Really. The best model is the simplest model that gives you the information you need to make a specific decision.
So it's about fit for purpose, not absolute fidelity.
Exactly. If a quick back-of-the-envelope calculation tells you design A is better than design B, and a super complex, week-long simulation tells you the same thing, you probably wasted a lot of time and effort on the complex model for that particular decision. It's always a trade-off. Fidelity versus the effort needed.
That really changes how you think about modeling. It's a tool for decision-making, not just description. So when we build these dynamic models, say for a suspension system or an electric circuit or a fluid flow, is there a unified way to approach it?
Yes, and that's one of the really elegant things here. The unified approach uses what are called ideal elements, and these are all based on the concept of energy.
Energy flow and storage.
Precisely. To model energy properly, you need a pair of related variables. The source material calls them a through variable and an across variable.
Okay, explain those.
Think about electricity. The through variable is the current, how much charge flows through a point per second. The across variable is the voltage, the potential difference across 2 points that drives the current. You need both flow and potential for power.
Like force and velocity in mechanics. Or flow rate and pressure in fluids.
Exactly. Force is through, velocity differences across, flow rate is through, pressure differences across. It's the same fundamental pairing.
And what do these ideal elements represent?
They do one of two things. They either store energy or they dissipate it. Energy storage elements are called T-type or A-type. Think springs storing potential energy, depends on displacement, across variable, or masses storing kinetic energy, depends on velocity, a through variable.
And dissipation.
Those are D-type elements. Dampers in mechanical systems, resistors in electrical systems, they turn useful energy into heat, basically.
Okay, so we have these building blocks. How do we connect them?
Using system relations, which are just the interconnection laws, there are two kinds. Continuity relations apply to those through variables. They ensure things like dynamic equilibrium, Newton's laws, Kirchhoff's current law, sum of flows into a junction is zero.
Makes sense. And the other kind?
Compatibility relations, these apply to the across variables. They usually represent geometrical constraints or things like Kirchhoff's voltage law. The sum of voltage drops around a loop is zero.
And the beauty of this.
Yeah.
Why is this unified approach so powerful?
This is the really cool part. When you find different physical systems, one mechanical, one electrical, maybe one fluidic, that end up having the exact same generalized mathematical model using these elements and relations, they're called analogs.
Meaning the math sees them as identical.
Fundamentally, yes. The math is telling you that, say, a simple spring mass damper system behaves exactly like an electrical RLC circuit. The underlying dynamics are the same.
Wow.
And this is incredibly useful, especially for modern systems that are often hybrids, part mechanical, part electrical, maybe with fluid or thermal elements too. This unified modeling lets you handle the whole thing consistently.
That's a powerful concept. Okay, so we have this elegant, hopefully simplified model. The next logical step is control, making the system do what we want. What's the standard setup for a control system?
The classic structure, the one you see everywhere, from thermostats to cruise control to industrial robots, is the feedback control loop.
Feedback. Okay, components.
You start with a command that's the desired value, what you want the system to achieve. Then you need an error detector. This compares the command to the actual measured output of the system.
The difference is the error.
Right, that error signal feeds into the controller. This is the brain, the logic element containing the control algorithm. The controller calculates a control signal, sends it to an actuator, that's the muscle, like a motor or a valve.
The thing that actually affects the system.
Exactly. The actuator acts on the plant, which is just the term for the system you're trying to control. And then, crucially, you measure the plant's output and feed it back to the error detector, closing a loop.
So the goal is always to drive that error signal towards zero.
That's the fundamental job of the controller, yeah. Keep the output close to the command.
Let's focus on that controller logic, the algorithm. We hear PID mentioned all the time. Why is PID control so dominant? And what are you trying to achieve when you design one?
PID, proportional integral derivative, it's just ubiquitous. It's popular because it tackles the main control objectives pretty effectively and intuitively.
Which are?
Typically, you have three main goals. First, minimize the steady-state error. You want the system to eventually settle exactly at the target value. Second, minimize the settling time. How quickly does it get there? And third, minimize overshoot. You don't want it to swing wildly past the target before settling down.
And each letter in PID addresses one of these.
Broadly speaking, yes. The proportional P term gives you a basic response proportional to the current error. The integral action is the key for eliminating that steady-state error. It keeps accumulating the error over time, providing an automatic reset that pushes the system until the error is truly zero.
And the derivative.
The derivative D action provides damping. It looks at the rate of change of the error, so it anticipates future error, helping to handle sudden changes or oscillations. Often, this is done using velocity feedback, like measuring motor speed with a tachometer.
Okay, PID seems straightforward.
Yep.
But you mentioned the integral term. The sources flag a specific problem with it. Reset windup or integrator buildup. What's that about? Sounds painful.
It can be a real pain point, yeah. Reset windup happens when your actuator, the motor, the valve, whatever, hits its physical limit, it gets saturated.
Like telling a motor to go faster than it physically can.
Exactly. Imagine commanding 120% power when it maxes out at 100%. The error signal, command minus actual, is still there, telling the controller, we're not there yet. So the integral term, whose job it is to accumulate error, it just keeps accumulating. It winds up demanding more and more control effort that the actuator simply cannot deliver.
Uh-oh, what happens then?
Well, while the actuator is saturated, nothing much changes. But later, when the system conditions change, maybe the command drops or the disturbance goes away and the system can start responding again, you've got this huge stored up value in the integrator.
Like a tightly wound spring.
Good analogy. That wound up value has to unwind, and it forces the actuator to keep pushing hard even when it shouldn't. The result is usually a massive, undesirable overshoot of the target value before things finally settle down. It really messes up the performance.
So managing that windup is a key design challenge for controllers with integral action.
Absolutely. You often need specific anti-windup logic to prevent the integrator from accumulating excessively when the actuator is saturated.
Okay, moving beyond PID. You mentioned the world's gone digital. How has digital control changed things, especially for more complex systems?
Digital control just offers so much more flexibility and power. You can implement much more complex algorithms, and importantly, you can often handle system nonlinearities more directly.
Nonlinearities, like things that don't behave in a simple proportional way.
Right. Friction, changing inertia, aerodynamic drag. Lots of real-world systems are nonlinear. A great example of using digital control to tackle this is the computed torque method, often used in robotics.
How does that work?
Well, a robot arm's dynamics are highly nonlinear. Its inertia, the effect of gravity on it, it all changes drastically depending on the arm's position and speed. It's complex.
I can imagine.
So the computed torque method uses the robot's dynamic model inside the controller. In real time, it calculates the expected nonlinear torques, especially those due to gravity and Coriolis effects, and then it actively cancels them out by adding opposing torques through the motors.
So it computationally removes the nonlinearity.
Essentially, yes, it linearizes the system on the fly. What's left is a much simpler, effectively linear system, which can then be controlled very easily and accurately using a standard linear controller, like a PID. It's a clever way to use computing power to simplify the control problem.
That's fascinating. Using the model to actively fight the complexity. Okay, so we've designed the system, modeled it, created this brilliant controller, but it all relies on measurement, right? We have to know what the system is actually doing. And measurements aren't perfect. Let's clarify. What's the real difference between accuracy and precision? People mix those up.
They do. They're related, but distinct. Accuracy is about how close your measurement reading is to the actual true value of whatever you're measuring.
Like hitting the bullseye on a target.
Exactly. Precision, on the other hand, is about repeatability. It's the degree to which multiple readings agree with each other.
Like all your shots landing very close together, even if they're not near the bullseye.
Perfect. So you can have high precision but low accuracy. All your measurements are tightly clustered, but they're all wrong by the same amount.
And high precision doesn't automatically mean you're accurate.
Not at all. To get accuracy, you need proper calibration against a known, trusted standard, something traceable back to a national standard, like NIST in the US.
Right. And another measurement issue is when the act of measuring changes the thing you're measuring. The source calls this loading. Can you give us an intuitive feel for that?
Sure. Imagine you have a tiny cup of very hot coffee and you want to measure its temperature. If you stick a big, cold metal thermometer into it.
The thermometer itself will cool the coffee down.
Exactly. The thermometer draws heat out of the coffee, so the temperature you read is lower than the coffee's original temperature. The measuring instrument has loaded the system, altering the quantity it was trying to measure.
How do engineers think about this technically?
It's often framed using impedance concepts. Impedance is like a generalized resistance to effort. The key idea is, if you're measuring an effort variable like voltage, pressure, or force, the input impedance of your measuring instrument needs to be much, much higher than the output impedance of the thing you're measuring.
High input impedance for the meter.
No way. Think of voltage. An ideal voltmeter has infinite resistance, impedance. You connect it across 2 points. If it had low resistance, it would draw significant current, changing the voltages in the circuit you're trying to measure. By having very high impedance, it draws almost no current, so it doesn't disturb the circuit voltage as much. The measure value depends on the ratio of those impedances.
How does that translate to mechanical systems, say measuring force?
Well, in mechanics, the analogous concept to impedance for static measurements is often stiffness. Imagine using a load cell, which is essentially a calibrated spring with stiffness, to measure the force in a structure.
Okay.
If the structure itself is very flexible, meaning it has a low output stiffness, and your load cell is relatively stiff, inserting the load cell actually changes how the structure deforms under load.
Because you've added another spring in series,
Yes.
essentially.
Yeah, precisely. Which means the force indicated by the load cell might not be the same as the force that would have been there without the load cell. To avoid this loading effect when measuring force, your load cell needs to be significantly stiffer than the system it's placed in. Its impedance needs to be high relative to the system's output impedance.
So the instrument shouldn't significantly alter the system's behavior. Makes sense.
Okay.
Okay, last piece. Error analysis. We know measurements have errors. How do engineers figure out which measurements they need to be most careful about, where to focus their effort?
This comes down to understanding error propagation, how small uncertainties in your individual measurements combine to create uncertainty in your final calculated result.
Got an example?
The classic one is measuring the acceleration due to gravity, dollars, using a simple pendulum. The basic physics tells us the dollars is proportional to the pendulum's length, divided by the square of its period, $2.222. So dollar impromptu LT22.
Okay, measure length, measure time period.
Right. Now, suppose you can measure the length dollars with some probable error and the period dollars with some probable error. How do these errors combine to affect the error in your calculated dollars, let's call it ED?
Oh.
The formula for the probable error, using standard propagation of uncertainty methods, shows that ED is roughly proportional to the square root of EE dollars plus 2ET $2.
Wait, there's a $2 in front of the time error?
Yes. And notice the errors are squared. That factor of 2 comes from the fact that $2 is squared in the formula for $2. When you square that term, 2 ETO dollars, you get $4 ET2.
So the error in the time measurement contributes 4 times as much to the final error variance as the error in the length measurement.
Exactly. That's the crucial insight. Because the period dollars is squared in the physics equation, uncertainty in measuring dollars has a much larger impact on the final uncertainty in dollars than the uncertainty in measuring dollars.
So if you want to improve your measurement of dealers, you should just spend way more effort getting a precise measurement of the time period than the length.
Absolutely. That's where you'll get the most bang for your buck in reducing the overall uncertainty. You focus your precision efforts on the most sensitive parameters, the ones with the highest exponents or largest influence in your calculation.
That's a really practical takeaway.
Yeah.
Okay, this has been quite a journey. We've gone all the way from the high-level need for systems thinking and getting requirements right.
Down through the elegance of unified modeling, using those ideal elements and analogies.
Then into the practicalities of control, PID, its strengths, pitfalls like reset windup, and even advanced techniques like computed torque.
And finally, landing on the hard reality of measurement accuracy versus precision, loading effects, and crucially, how error analysis tells us where to focus our efforts.
It really paints a picture of the whole systematic framework engineers use to tackle complexity and actually deliver working systems.
And maybe one final thought underpinning all this structure, all this math, we have to remember the human element. The source material actually points this out.
How so?
It mentions common human cognitive biases, things like availability bias, over-relying on recent info, anchoring, like we discussed with requirements, selective perception, confusing facts with values. These biases can easily lead to flawed judgments, even with smart people.
So the systems engineering process itself helps counteract that.
That's the idea. By demanding an explicit, structured, iterative process, defining requirements clearly, modeling assumptions, analyzing trade-offs, checking results, systems engineering provides a framework to help detect and correct these potential human errors. It pushes us beyond what unaided intuition alone can achieve, improving the quality of both the design and the decisions made along the way.
A structured way to keep ourselves honest, basically. Great final point. Keep your nuts torqued and spring hard design junkies.